Okay, I'm going to do something different in this session of the masterclass. What I'm going to do is talk about simplifying expressions, but I'm going to do that using the whiteboard and also doing some live coding. So let's get started and let's look at a particular example of an expression. You can see an expression, I've called it expression 2, it's in the code. And here is the expression written out in printed format, and here's what it looks like if we draw it as an expression tree. Now what we can see in this is that there's a whole lot of simplifications that we might do in here. First of all, we can simplify something like this. We have a multiplication by 1. 1 times b simplifies to be b. We also have another of those down here, another multiplication by 1. We've got a multiplication by 0 here, and that simplifies simply to 0. And then finally, hidden at the top, we have an addition of 0. Because if this whole part of the tree simplifies to 0, we can then simplify the whole thing to what we see there. Okay, so we have a number of rules that we can apply. 1 times something is something, 0 times something is 0, and 0 plus something is the thing we started with. So what I'm going to do to start with, I'm going to do a bit of coding. I'm going to show you how to do those simplifications. So let's do 0, 0, add. And what we say there is if we have an add, and we have something like an expression e, and we're adding to that the number 0, we can simplify that to e. In a similar way, if we have the other way round, oh, and I've made a mistake already here, I should have put that in parentheses. So there we are, that looks a bit better. It's turning out, this is the trouble with live coding. Let's make sure we have some parentheses there. We have add, and then we have the number 0 on the left, and then we have an expression e on the right. That simplifies, that simplifies again to e. And then, according to this rule, anything else, call it e, will be unsimplified. So that remains as e. Now, in a similar way, we can think about multiplying by 1. So multiplying by 1, mul o, let's say. If we apply that to a multiplication of e and the number 1, num comma 1, what happens there is that simplifies to e. Now, why have I called it O? O for 1, right, of course, yes. And similarly, if we multiply the number 1 by any expression e, we get also simplifying to e. And again, finally, if we do any other multiplication, this rule doesn't help. So what we're doing is just writing the rule that does the simplest possible simplification. So we've done the 0 addition, we've done multiplication by 1. The final rule we've got is multiplication by 0. Mul z, let's call it. And here we have a multiplication of an expression e. Well, in fact, it doesn't matter what the expression is, and the number 0 simplifies to 0. Sorry, num 0. In a similar way, multiplying num 0 by any expression at all, sorry, I'll use a wildcard so we don't get any warnings about unmatched expressions, gives us num 0. And then finally, as we had in earlier cases, we could see that if we simplify any other expression, we will get that same expression back. So let's have a look at what we've got here. We've got our 3 functions, 0a, mul 0, and mul z. Let's just compile those, make sure that they compile okay. And okay, they do. So what we have here are three functions which we can use to simplify very specific expressions. But as you can see in the example we've got here, we need to apply the simplifications across the tree. We need to make sure that we simplify using one rule here, using another rule there, using another rule at the top. And we need to make sure that we do them in some order, because as I said at the beginning, we had to apply this rule here, the rule that says multiply by 0 reduces the whole sub-expression to 0, before we could use the plus 0 rule at the top. So how are we going to write a simplification? Well, what I'm going to do is write a very general simplification that applies a set of rules across a whole formula, a whole expression. And what I'm going to do is, first of all, combine my rules together. So I'm going to write a function called compose, which takes a list of functions and applies all of them, one after the other. So what compose will do is, if I apply it to no functions at all, I apply it to the empty list of functions, what it will do is return me a function that simply is the identity. It doesn't make any transformation at all. So what this does is takes an expression E and returns the same expression. Okay, so that's the base case. But what about the case where I've got a number of rules? I've got a rule, and then I've got some other rules. What do I do here? Well, what I do is I return a function again, and what does that function do? It takes an expression, and what that expression does is to apply the rule, the first rule, and then to that result, it applies the result of composing all the rest. So what we've got here is a function the function compose applied to the list of rules. You can see it indicated by the blue here. And then that is a function, and we apply it to the result of applying rule to E. So we first apply rule, then we apply all the rest of the rules. And what we've got here is a very nice example of what's called a higher order function. And it's higher order in two ways. It takes a list of functions as argument and returns us a function as a result. So let's save that. Let's check to see that this compiles. And it does. So what we can do is we can put together our three rules. We might throw some more rules in later on. But at the moment we've got three rules. We'll tie those in together into one big function. We've got a nice piece of modularity here. You can see we've got the three separate rules, one for reducing multiplication by 0, and so on. And what we can do is build those into a single list of rules, a single function. And we'll call it rules. And well, let's write the list. So what we have is the function 0a, with arity 1, the function mul 1 with the arity 1, and the function mul z with the arity 1. So here we've got a little list of functions, and what we will do is compose those together. And once we've got that composition, we'll think about how to apply them to the whole tree. And what should we do about the simplification? Well, let's again think about. Oh, we've got a problem here. Oh, I've got a problem because I didn't put a fun there. And then that should, there we are, that problem has gone away. I'm using flymake here, so you're seeing the wiggly line, and that's showing that it wasn't compiling. So when I don't have any red lines, it should compile okay. But let's think about what we want to do about simplification. And what we'll do with simplification is we'll take a function, which will be our rules, all composed together, and how do we apply that to an expression? Well, what do we do about simplifying an add? let's think about what we do here. Because what we want to do, guided by what we had in our example here, is we want to simplify bottom up. We want to simplify the inner expressions first, and only when those are simplified, we want to apply the simplification at the top level. So what we want to say is something like this. Take f and apply it to the result of adding the simplified versions of E1 and E2. Whoops, simp f E1 and simp f E2. Okay, oops, I keep getting the wrong brackets. So what have we got here? So the result is that, and we apply f. So we've simplified the left sub-expression, simplified the right, and what we then do is simplify the whole expression that they form. Okay, now I'm going to cheat a little bit here and copy and paste this and change the add to mul, because that's the simplest way of dealing with that. And then, actually, is there any simplification we can do with the others? Well, the answer is actually there's none. So any other expression will simplify to itself. So there we've got this nice simplifier. It's working bottom up. And what we've done here, it's interesting to see, we've used a higher order function to separate the way that we do the traversal of the tree, this simplification function here, from the actual simplification that we do, which is the compose. So we're going to say simplify is defined to be, simplify of an expression E is defined to be simp, our simplifying strategy applied to compose of rules, because that's our list of rules, and that gives us a single simplifying function and E. And there we have our definition of our simplification. And we've got a problem here. Why have we got a problem here? Compose of rules should be fine. The function simp2 is undefined. Why is it saying that? Because I'm missing an argument here. So in fact, it doesn't matter what the simplifying function is there, it simplifies to nothing takes place there. So we don't need to match on the simplifying function. I can just put a underscore f there just to show it's the function we're missing there. And now we've got our simp defined, we've got our simplify, and let's see, this should compile. Let's see if it compiles. C expr. And then let's give this a go and see whether what we want to do is print an expression. Oh, sorry, that's expr print of expr simplify of expr expression 2. Okay, so we can see we've got our compose function, which allows us to put the rules together, and now we've written our simplification simp that applies a simplifying function across the tree, bottom up, applies to the sub-expressions first, and then applies the function at the top level. And we've also got the function simplify that puts together our set of rules, which we've composed into one rule, and applies it across an expression. And what we can see here in the evaluator box, I've said, let's print the result of simplifying the expression 2, which is our expression here, and you can see, indeed, we get as a result the value b. So we've got the 1 times b is simplified to b, the whole tree here, that is simplified to b, but then the whole tree will here simplify to 0, and we have b plus 0, which itself simplifies to b. So we've got that simplification. The rules are applied bottom up using that strategy. Now, something else we could do, just as a final step, we could think of simplifying situations where we had something like a tree that had perhaps plus 1, 2, and a variable v there. We could simplify that by evaluating the purely numeric part and reducing something like that to 3 plus v. And all we'd need to do if we were to do that would be to take the simplification and add it to our list of rules here. Because the rules are composed together, and what we do is make sure if we have a purely numeric part of a tree, we evaluate it and put the result there in place of the whole tree. So we could add that as an extra simplification, and I'll leave that to you as an exercise. Also other simplifications you can add, but what's nice about the approach here is it's completely modular. You write a new simplification, like one of these rules, mul O or mul Z, add it to the list of rules here, and you've got that more powerful simplifier working over your expressions. So I hope that's shown you a way that you can use the power of higher order functions, treating functions as data, build a list of them, compose them all together, and make that an argument to another function to give you modularity. We've separated the particular simplification from the simplification strategy, which here is bottom up. And so we get that modularity, which you wouldn't get in a first-order language, where we'd have to write a particular simplification function where the strategy was burnt into the function. So it's a nice example to end. Higher-order functions, both as data, arguments and results of functions, and the extra power and elegance, modularity that those bring. So I'll draw this live coding to a close here, but encourage you to take the example on and see how much further you can go with that. Okay, thank you.